If your team builds on AI agent frameworks, 3 of them ship the exact same architectural flaw in 14 months. Today, we're breaking down the one in Microsoft Semantic Kernel, not just the vulnerability itself, but the design pattern that made it inevitable. This is the isolation principle your threat model is probably missing. By the end of this, you'll have a new threat modeling question for every AI agent component in your stack. First, the vulnerability itself and why it matters beyond a single CVE. Then the design pattern and why it keeps showing up. We'll walk through root cause, update your threat model, and close with prioritized actions you can take this week. A single API call, that's all it takes. CVE-2026-26030 is a critical remote code execution flaw in the Semantic Kernel Python SDK, published February 10, 2026, fixed same day in version 1.39.4. This is not just another CVE. It's the third AI agent framework to ship the exact same category of flaw in 14 months. Semantic Kernel in February 2026, LangChain in December 2025, LlamaIndex in early 2025. Same architectural mistake, different components. The CVSS score is 9.9 critical. The GitHub CNA published 10.0, but the actual vector, scope changed, privileges required low, calculates to 9.9 under the CVSS 3.1 formula. Critical, either way. What makes this one architecturally significant? A low privilege authenticated user, trial account, standard API key, compromised credential, can reach full remote code execution through the filter API. Not through the model, not through prompt injection. Through the VectorStore's query interface. The filter API is a code execution surface, and the patch applies a block list of dangerous attribute names. We'll cover why that's not enough in the remediation section. The architectural fix requires isolation, separating the query evaluator from the Python runtime entirely. That architectural fix requires understanding the pattern. It has a name, the Framework-Internal Eval Surface. It appears when an AI framework's query interface accepts caller-supplied strings and resolves them through the host language's native attribute access, inheriting the interface without inheriting the isolation. Look at the timeline. Semantic Kernel, February 2026. Filter evaluation resolves caller-supplied field names through Python's attribute access mechanism. That's the one we're analyzing today. LangChain, December 2025. CVE 2025-68664. CVSS 9.3. Serialization treated LLM influence data as trusted framework objects. Same class, user-controlled data reaching the host language's execution layer through a framework interface. LlamaIndex, early 2025. CVE 2025-1793. Critical. SQL injection in VectorStore query interfaces. Unvalidated inputs reached SQL query construction. The oldest form of the pattern, surfacing in the newest category of software. 3 major frameworks, 14 months. All allowing user-supplied strings to reach host language execution contexts. This is not a coincidence, it's a class vulnerability. AI agent framework authors reached for host language dynamism when building query abstractions, inheriting the interface pattern from databases without inheriting the isolation guarantee that makes it safe. So with that pattern context, let's walk through the mechanics. The advisory covers the full technical detail. We're focusing on the structural points. On the left, the exploitation path. An attacker authenticates with any low privilege account. They submit a filter expression containing Python dunder attributes, _class, _import, _built-ins, as field selectors. The filter evaluation path resolves these through Python's object attribute access, traversing the object model to reach the import system. On the right, the impact. The attacker achieves arbitrary code execution as the agent process OS user. Every API key, database credential, and service token loaded in that process is accessible. The agent's full memory, conversation history, system prompt, stored memories, is readable. And the host file system and network are exposed at the process privilege level. The vulnerability is classified CWE94, code injection, at root cause. And that's the key point. This isn't a coding mistake. The design placed the query evaluator inside the Python runtime. The code does exactly what the design specified, and the design is vulnerable by construction. What went wrong here wasn't a coding error. It was a design decision that made every correct implementation of this interface vulnerable. Before we get to the mitigations, one more look at the root cause. On the left, what went wrong? The InMemoryVectorStore filter resolved caller-supplied field names through Python's getAff mechanism. There was no boundary between the query language and the host runtime. Contrast this with SQL parameterization, where the query engine parses expressions using its own type system, with no path to the host language. That isolation is the structural guarantee that makes SQL injection impossible within the parameterized boundary. InMemoryVectorStore had no equivalent boundary. On the right, what correct looks like. First, a schema-based field allow list at the evaluation boundary. Validate every caller-supplied token against a static, developer-authored set of valid field names before it reaches any evaluator. Second, an isolated evaluator with no path to the Python runtime, a purpose-built parser whose grammar is limited to schema fields and comparison operators. Third, apply the same SQL parameterization discipline to every AI agent filter and query API. The invariant, a caller's ability to name a field, must not be equivalent to accessing the Python runtime's object model. Here's a test you can run in your next architecture review. Most teams review AI agent systems for prompt injection and output handling. Vector store filter APIs are treated as infrastructure, plumbing, not attack surface. This CVE establishes that filter interfaces mapping caller-supplied strings to host language objects are code execution surfaces, full stop. Authentication is not a sufficient gate. PRL means any standard user can reach this surface, a trial account, a registered user, a compromised credential. Apply authorization at the filter parameter level with a static schema allow list, independent of authentication status. And here's the one that surprises most teams. In-process storage does not carry lower risk when the query interface is the attack surface. Eliminating the network hop does not change the semantics of a filter that resolves strings against host language objects. If your agent constructs filter expressions from LLM output, the available evidence suggests that's a plausible prompt injection chain, combining LLM-08 exploitation to reach RCE. But it's not a confirmed exploitation technique for this specific CVE. Treat LLM output as untrusted to all downstream filter parameters. So, you've seen the design failure. Now the question is, what do you do Monday morning? We've broken this into 3 tiers, and the first one has a 7-day clock. Immediate actions within the next 7 days. Upgrade the Semantic Kernel Python SDK to 1.39.4 across all environments today. If any environment cannot be patched immediately, block or require explicit authorization for API calls carrying filter expression parameters to InMemoryVectorStore endpoints. If you consume Semantic Kernel through a third-party vendor product, verify with your vendor that their release incorporates Python 1.39.4 or later. Don't assume it, confirm it. One more thing most teams get wrong here. Add CVE-2026-26030 to your vulnerability management backlog, but scope it to the architectural remediation, implementing the schema-based allow list, not just the patch. The patch applies a block list. A block list can be bypassed if an attacker discovers names not on the list. An allow list rejects anything not explicitly permitted. But the full architectural correct is the isolated evaluator, which we covered in the root cause section. Here's the full roadmap across 3 tiers. Immediate, 0 to 7 days. Upgrade the SDK and block unpatched filter API access. We just covered this. Short-term for mid-maturity teams, add the filter API to your threat model as an injection surface and implement a schema-based field allow list at the application layer. This is the critical architectural step. Validate caller-supplied strings against developer-authored field names before they reach any evaluation path. Extend your SCA scanning to flag vulnerable semantic kernel versions automatically, and audit any application layer code that constructs filter expressions from untrusted inputs. The framework patch addresses the framework's evaluation path. It does not protect application code that builds equivalent injection surfaces above the framework. Strategic for all organizations on a longer horizon. Add filter and query interface injection review as a mandatory step in your threat modeling phase for every AI agent framework component. The question to ask at design time: does this component accept caller-supplied strings and resolve them through the host language's object model? If yes, this CVE maps to 3 OWASP categories, and each mapping carries a distinct implication. First, LLM-08 2025, Vector and Embedding Weaknesses. CVE-2026-26030 is a direct LLM-08 instance. The exploit targets the vector store's filter API, bypassing the model entirely. If your LLM-08 threat modeling has addressed data poisoning, but not the filter API as a code execution surface, add that to your next architecture review. Second, AO5 2025, Injection. AO5 covers attacker-supplied data interpreted as a command. This maps squarely filter attribute names resolved as Python object paths, not data tokens. The SQL injection discipline, validate against a schema allow list, never pass user data directly to an evaluator, applies without modification. And third, AO6 2025, Insecure Design. The architectural failure where no correct implementation compensates for a missing structural control. The filter evaluates expressions inside the trusted execution context, vulnerable by construction. The patch adds a block list. The architectural correct requires redesigning the evaluation path. If you only remember one thing from this analysis, make it this. On the left, the isolation principle. Any interface that maps user-supplied strings to host language object access is an injection surface, regardless of how the API documentation labels it. A filter expression in a vector store is functionally equivalent to a query string passed to an interpreter. Patching the framework fixes the framework's threat model. It does not fix your application's threat model. Application code that constructs filter expressions from untrusted inputs may reintroduce the pattern independently. On the right, the class perspective. This is not an isolated bug. It's a class vulnerability. 3 major frameworks shipped variants in 14 months. AI agent framework developers are rediscovering the injection vulnerability class that web developers resolved through parameterization and sandboxing a generation ago. The teams that internalize the isolation principle, that every interface accepting caller-supplied strings and resolving them via language-native attribute access is an injection surface, will catch the next variant before it ships. The lesson from CVE-2026-26030 is not about semantic kernel specifically. It's about a design assumption that is wrong every time it appears, that accepting user-controlled strings and resolving them through the host language's object model is safe because the interface is labeled filter rather than eval. AI agent framework developers are learning it again in Python in VectorStore query interfaces. The separation between query language and host runtime is not optional, it is the structural guarantee. Teams that internalize this will apply the right threat modeling question to the next framework component before it ships. That is what separates a team that patches this CVE from a team that would have prevented it. Full references are linked in the article and in the video description. 3 frameworks, 14 months, 1 pattern. Now you know how to spot the next one. The full written analysis with all references is on dcicyber.com and linked in the video description. If you found a trust boundary failure in your own AI agent stack, especially one that looked like infrastructure until you tested it, drop it in the comments. If these architecture breakdowns help your threat modeling, subscribe. We cover a new vulnerability class every week. Thanks for watching.